Hey guys, welcome back. So in the last video, we were talking about selection sort algorithm. Hope that algorithm is clear. Now in this video, let's see a very similar type of sorting algorithm called insertion sort. So what we do in insertion sort is somewhat similar to what we saw in selection sort. Let's see how it works. So in insertion sort, we take the given array and we divide it into two parts, sorted and unsorted array. Then we go to the unsorted array and take the first element from it, and then we find the correct position of that element in unsorted array and we place it in the unsorted array. So if you remember, in selection sort also we were trying to do something very similar. We divided the entire array into two parts, sorted and unsorted. In unsorted array, we picked one element and we made sure that it is put in its correct position. But in case of insertion sort, we do it specifically for the first element in the unsorted array. Now once this step is done, we keep on doing the same step until unsorted array is not empty. And after completing all these three steps, we get our final answer, which is having a sorted array, and unsorted array of course will be null in that case. So now let's try to understand this algorithm using a very simple example. So here we have an array which is of course unsorted one, and now let's try to apply insertion sort on this array. So as we said, first we have to divide this array into two parts, sorted and unsorted array. So initially sorted array will not have anything, it will be blank or null. Unsorted will have all the elements in the current array. Then we go to the unsorted array and pick the first element and put it in its correct position in the sorted array. So the first element in the unsorted array is 30. So we'll take it and put it in the sorted array. Now since in the sorted array there is no element, so we can simply put the 30 over here. We don't have any other comparison to be done in sorted array. So after this step, this is how the array will look like. So sorted array is having one element 30, unsorted array is having all these elements. Now we have to iterate this second step again because unsorted array is not empty right now. So again we go to unsorted array, take the first element which is 10 and put it in its correct position in the sorted array. So in the sorted array we have only one element 30. Now how do we find the correct position of this element in the sorted array? Simple. We just have to compare this element with all the elements in the sorted array starting from last. And whenever we find that this element is bigger than any of the element in the sorted array, that is the correct position of the element in the sorted array. So right now we see that 10 is smaller than 30. So both of these needs to be swapped. So 30 comes here and 10 goes there. And now since there are no more elements, no more comparison is required. So after this step, this is how the array will look like. Sorted array is having 10 and 30. Unsorted array is having these 4 elements. Now again we do the same step. We go to unsorted array, take the first element which is 50. And we need to put it at its correct position. So 50 is more than 30. So that means 50 is already at its correct location. So this is how the array will look like after the third iteration. Sorted array is having 10, 30, 50. Unsorted array is having 20, 60, 40. We again repeat the same step. Go to unsorted array, take the first element 20. Put it at its correct position in the sorted array. So for that we have to compare 20 with all these elements. And whenever we find that there is some element which is smaller than 20, that is the correct position of this number. So 20 is smaller than 50, so it needs to be shifted over here. So 50 comes here and 20 comes here. Now again we do the same thing. 20 is less than 30, so it needs to be shifted over here. So 30 comes here, 20 comes here. Now 20 is greater than 10, so we'll stop. So we'll not do any more comparisons. So after this iteration, this is how the array will look like. Sorted array is having 10, 20, 30, 50, unsorted 60, 40. Again we'll do the same step. We'll go to the unsorted array. First element is 60. Compare it with the previous element. 60 is more than 50, so nothing needs to be done. So now we have only one element in the unsorted array, so we'll again do the same step. So I will try to find the correct position of this number. So 40 is less than 60. So we need to exchange these numbers. So 60 goes over here, 40 comes here. Again we do a comparison. 40 is less than 50. So these needs to be exchanged. So 40 moves over here. Now we again do a comparison. 40 is more than 30. So no more comparison or exchange is required. So this is our final answer. So we have found the correct position of 40, which is here. So now if you see, we have all the elements in the sorted array and unsorted array is blank. And hence this is our final answer. 10, 20, 30, 40, 50, 60. Fine. So that is how we do insertion sort on a given set of numbers. Now let's quickly see the algorithm for this sorting technique. So if we see this algorithm, we have two loops over here. The outer loop takes care of how many times the iteration needs to be run. So it needs to be run for n number of times, where n stands for the count of numbers that we have in our set. So in this case we have 6 numbers. Then we have an inner loop which takes care of all the comparison and swapping activities. Now since the algorithm is extremely simple, I am not going through each and every step out there. Please try to apply this algorithm on this set of numbers again. This will make sure that we understand this algorithm even more better. Now let's see the time and space complexity of this algorithm. So here we have a loop which runs for n amount of time, so it takes order n complexity. Similarly, here again we have a loop which approximately runs for n number of times. So again it takes order of n time complexity. Rest of the operations are all constant time operations because we are just doing some comparisons and doing some swap of a values, nothing more than that. So those are all constant time operations. So if you add all of them, we get order of n. Now since these two loops are nested, so we have to multiply them, so it becomes order n square. So time complexity is order n square. Space complexity as expected is order 1 because we are not using any extra space for doing this sorting algorithm. Fine. So that is all about insertion sort. Now let's quickly see when should we use insertion sort and when we should not use it. So in case if we cannot afford any extra space for doing the sorting activity, then insertion sort is a very good choice because it does not use any extra space. Also, in case if you want a simple implementation, insertion sort is good enough because the algorithm, as we have already seen, is very simple. The third important thing is when we have continuous inflow of numbers, in those cases insertion sort is the best sorting algorithm because every time a new element comes in, we make sure that it is immediately placed at its correct position, because of which our array will always be sorted. So insertion sort is great for those situations. Now when we should not be using insertion sort, that is when the average case is expected to be good one, like order n or order n log n. As we have already seen, insertion sort runs for order n square time, which is way higher. So in case if you want an efficient algorithm, insertion sort might not be the greatest of the choice. Fine, so that is all about the insertion sort algorithm. In the next video, let's see one more sorting technique.